Sometime in the ninth century, deep in the mountains of what is now central China, a small group of Taoist alchemists were working on something that had nothing whatsoever to do with fighting wars. They were trying to achieve immortality. Convinced that some precise blend of minerals could produce a drinkable elixir capable of extending life indefinitely, they spent years combining, heating, and testing whatever raw materials they could get their hands on, following formulas inherited from generations of medicinal and mystical practice before them. At some point, one specific batch brought together three particular ingredients: a nitrate rich mineral salt, charcoal, and sulfur. Instead of granting anyone eternal life, that combination did something else entirely. It caught fire violently and blew apart. Historical accounts from that era describe singed eyebrows, scorched robes, and at least one workshop burned to the ground, which tells you almost everything you need to know about how that first genuine encounter actually unfolded. Nobody standing in that room had the faintest intention of inventing a weapon. They named the substance fire drug, a label that still quietly preserves its true original purpose as a failed medicine rather than a future tool of conquest. And yet that single accidental eyebrow-singeing batch of failed immortality medicine eventually became the most consequential chemical discovery in the entire history of human warfare, the direct ancestor of every cannon, musket, and firearm that would ever exist. So, how exactly did humanity travel the distance between a failed potion in a Chinese alchemy workshop and the modern firearm? The full path runs through hollow bamboo poles lashed to spears, at least one real 14th century military manual describing weapons that sound almost like science fiction, a genuine surviving bronze artifact you can still see in a museum today, and roughly 7 centuries of small, practical improvements carried across an entire continent by conquest, trade, and plain curiosity. If puzzles like that, tracing something enormous back to a tiny, accidental origin, are why you keep coming back to this channel, subscribing just means the next one arrives without you having to go searching for it. Start with the basic chemistry, because understanding it explains everything that follows. That original mixture combined potassium nitrate, generally known as saltpeter, with charcoal and sulfur in a rough ratio of roughly 75 parts, saltpeter to 15 parts, charcoal to 10 parts, sulfur by weight. The saltpeter acted as an oxidizer, releasing oxygen rapidly once heated and feeding an extremely fast combustion reaction that produced a sudden, violent expansion of gas. That expanding gas is the entire secret behind everything this substance would eventually be used for, from launching fireworks into a night sky to eventually launching a metal projectile through a tube with enough force to punch straight through armor. The chemistry itself never really changed across the centuries that followed, remaining fundamentally the same basic reaction from start to finish. What changed, again and again, was everything built around that reaction: the containers holding it, the mechanisms igniting it reliably, and the purposes people eventually decided to put it toward. In its earliest documented uses, this new substance was not weaponized at all. It showed up in fireworks, smoke signals, and festival displays, exactly the kind of celebratory, decorative use you would expect from something first discovered by monks chasing eternal life rather than military engineers chasing battlefield advantage. That changed once military commanders got a serious look at what this volatile substance could actually accomplish. Sometime between the 10th and 12th centuries, Chinese engineers developed a device called the fire lance, and the underlying design was about as simple as a weapon could possibly get. Take a length of bamboo, strap it securely to the end of a spear, pack the tube with the explosive mixture, and light it during close combat. The result was a polearm that sprayed flame and burning debris directly at anyone within arm's reach, turning an ordinary spear into something dramatically more frightening to face in hand-to-hand fighting. Defenders used fire lances during a major siege in the 12th century against attackers scaling their walls. And by every surviving account, the weapon performed exactly as intended, scorching and disorienting attackers in ways an ordinary spear simply could not. The psychological impact mattered just as much as the physical damage. Soldiers who had trained their entire lives to fight with blades and spears suddenly found themselves facing an enemy who could project fire itself. And that kind of shock carried real weight on a medieval battlefield, unsettling formations and disciplined ranks in ways a conventional weapon rarely managed on its own. Accounts describe defenders using these weapons specifically to break the momentum of an advancing charge, buying precious seconds that a spear alone simply could not have bought. Once this technology had proven itself in genuine, bloody combat rather than merely in theory, the pace of refinement picked up considerably, and each subsequent improvement followed a fairly logical next step from whatever design had come immediately before it, driven not by any grand strategic vision handed down from above, but by ordinary soldiers and craftsmen noticing a specific practical shortcoming firsthand and quietly working out a genuinely practical fix for it. Fire lance users began stuffing pellets and shards of broken pottery into the bamboo tubes alongside the explosive charge, turning a weapon that produced flame into one that also flung small projectiles outward with genuine force. That single change mattered enormously, since it shifted the weapon's core purpose away from pure intimidation and burning and toward actual physical, penetrating injury delivered at a distance, the foundational concept underlying every firearm that would ever follow it. There is a genuinely remarkable primary source from this general period worth knowing about directly. A 14th century Chinese military text, generally translated as the Fire Drake Manual, documented an entire arsenal of increasingly sophisticated gunpowder weapons in careful technical detail, including designs for early rocket-propelled arrows, floating naval mines meant to be triggered against enemy ships, and, most strikingly, a genuine multi-stage rocket concept, one rocket stage igniting a second stage after the first had burned out, centuries before anyone would formally apply that same layered principle to rocketry again. Reading through that manual today, it becomes obvious that Chinese engineers were not simply tinkering in isolation, workshop by workshop, hoping to stumble onto something useful. They had built an entire, deliberately documented field of applied gunpowder engineering, complete with detailed illustrations, material specifications, and step-by-step construction instructions meant to be passed down and reliably replicated by later generations of trained specialists, rather than rediscovered from scratch each time. That level of organized documentation is itself remarkable, considering how many other technologies from the same era survive only as fragments, guesswork, and secondhand description. The next real limitation was the bamboo itself, which simply could not withstand the pressure that more powerful gunpowder charges generated without splitting apart in the user's own hands. Once Chinese metalworkers learned to cast bronze tubes strong enough to safely contain that pressure, the hand cannon was born, a weapon that used expanding combustion gas to launch a single solid projectile with considerably more force and range than any bamboo fire lance ever managed. One of the actual physical objects from this exact transition still survives today, a bronze hand cannon recovered in Inner Mongolia and dated with real confidence to the very end of the 13th century, making it among the oldest confirmed firearms ever discovered anywhere on Earth. Holding an object like that, or even just seeing photographs of it, collapses the distance between an abstract historical narrative and a genuine, touchable artifact that some specific person once actually loaded, aimed, and fired centuries ago. Museum conservators have studied the barrel's bore diameter, wall thickness, and overall casting technique in considerable detail, and everything about its construction points toward a weapon that was already the product of real, accumulated engineering knowledge, refined through earlier trial and error, rather than a first crude prototype still fumbling blindly toward a working design. When the Mongols swept through China during the 13th century, they encountered these gunpowder weapons directly during major sieges, and the experience left a permanent impression. Rather than simply being defeated by the new technology, the Mongols absorbed it, and once they had conquered China and established their own ruling dynasty there, they carried gunpowder weaponry with them as their campaigns pushed westward across the rest of Asia and toward the Islamic world. This counts as one of history's more underappreciated technology transfers, since Mongol military campaigns functioned almost like an accidental delivery system, moving gunpowder knowledge across enormous distances far faster than trade caravans or diplomatic contact ever could have managed alone, spreading a distinctly Chinese invention across the entire breadth of Eurasia within only a handful of generations. Engineers, captured artisans, and skilled prisoners of war were routinely absorbed directly into Mongol armies as they advanced further west, meaning the underlying knowledge did not simply travel along as rumor or vague, secondhand description passed between merchants. It traveled as living, hands-on expertise instead, carried directly by the very people who actually knew how to construct, load, and operate these weapons in the first place, ready to demonstrate and teach the process the moment a new army required it. Gunpowder technology did not travel in a single straight line during this stretch, either. Alongside hand cannons, Chinese engineers also refined dedicated rockets and fire arrows, propelled projectiles that found real use not only across China but eventually in Korea and India as well. Moving along separate but overlapping routes from the path the hand cannon itself was taking westward. These rocket weapons never fully vanished the way the fire lance eventually did, once true firearms matured and made the older bamboo design largely redundant. Instead, rockets persisted as their own distinct branch of gunpowder engineering, one that would resurface centuries later in European warfare, again in colonial conflicts in India, and much later still in the earliest ancestors of modern military and even space rocketry. The story genuinely branches in two directions from that same original discovery: one path heading toward the gun, an entirely separate path heading toward the rocket, both rooted in the identical accidental reaction found by alchemists who wanted absolutely nothing to do with either eventual outcome. It is worth pausing on that fact alone, that a monk's failed attempt at eternal life eventually put a person on the moon by one branch of its family tree and toppled medieval castle walls by the other. Two wildly different destinations sharing the exact same chemical ancestor. From there, the technology spread outward along several overlapping routes at once, reaching the Islamic world and eventually Europe through a mix of military contact, trade, and the broader wave of cross-cultural exchange that defined the 13th and 14th centuries. Gunpowder was far from the only significant Chinese invention traveling westward during this same general period. Paper, printing, and the magnetic compass all moved along roughly the same trade and diplomatic routes across roughly the same stretch of centuries, part of a much larger, older flow of knowledge moving steadily from east to west long before anyone had a word for globalization or thought to track how ideas actually spread between civilizations. Once the technology reached Europe late in the 13th century, it landed inside a political and military system that gunpowder weapons would, over the following several centuries, permanently transform, gradually dismantling forms of feudal military power that had held remarkably steady for hundreds of years without any serious challenger. Some historians studying early European cannon design have pointed out that certain designs bear such a close structural resemblance to Chinese originals that a direct transfer of knowledge seems considerably more plausible than two separate cultures happening to invent nearly identical solutions independently. Early European hand cannons were crude, slow to reload, and genuinely difficult to aim with any real precision. Essentially, small cannons mounted awkwardly on the end of a pole, loaded from the open muzzle, and touched off with a smoldering ember. Yet, even in this primitive form, the weapon carried a psychological and physical impact. Traditional melee weapons simply could not match. Castle walls that had withstood traditional siege equipment for generations began falling to cannon fire, and mounted knights in heavy armor, the dominant military force across medieval Europe, found themselves increasingly vulnerable to a weapon that punched through steel regardless of how much of it a person happened to be wearing. The entire social and military order built around expensive, heavily armored cavalry began to wobble. Since a relatively cheap weapon in the hands of a far less expensively trained soldier could now neutralize an opponent who had spent a lifetime and a genuine fortune preparing for combat in the traditional way. The next genuinely important leap arrived late in the 15th century with the invention of the matchlock mechanism, and this single development finally turned gunpowder weapons from clumsy novelties into the actual backbone of organized infantry warfare across the continent. Earlier hand cannons required two hands and considerable careful coordination just to fire successfully. One hand steadying the weapon against a shoulder or hip, the other applying a burning ember or length of cord directly to a small touch hole at exactly the right instant, while somehow still aiming at a moving target. The matchlock solved this by attaching a slow-burning cord held inside a curved clamp directly to the weapon itself. Pulling the trigger lowered that already lit cord into a small pan of priming powder, igniting the main charge automatically and freeing the shooter to actually aim the weapon with both hands right up until the moment it fired. That may sound like a modest mechanical tweak, but it was genuinely transformative. The first mechanical firing device ever applied to a handheld weapon allowing a single trained soldier to fire with some real degree of aimed precision instead of simply pointing roughly in the right direction and trusting to luck. Armies that adopted it early gained a meaningful tactical edge over neighbors still relying on older, cruder designs, and that gap alone was often enough to decide the outcome of an entire regional conflict. The matchlock spread rapidly across Western Europe and beyond, adopted directly by Ottoman military units who incorporated it into their most elite infantry formations, refined into some of the most prized and precisely crafted firearms of the era. Once Portuguese traders introduced the design to Japanese gunsmiths on a small southern island, and eventually reabsorbed back into China itself in an improved form, developed there specifically to counter threats along the northern frontier, a genuinely fitting loop for a technology born in that same general region centuries earlier. There is a practical, less glamorous side to this story worth mentioning as well: the raw material itself. Saltpeter did not simply appear wherever an army happened to need it, ready and waiting in convenient quantities. It had to be harvested, often scraped painstakingly from nitrogen-rich soil, aging manure heaps, and damp cave deposits, then refined through a slow, genuinely labor-intensive purification process before it was clean enough for reliable, consistent gunpowder production. As European demand for gunpowder exploded alongside the spread of matchlock and later flintlock weapons, certain regions of the world became genuinely significant exporters of this one raw material. Parts of the Indian subcontinent, particularly the fertile region of Bihar, developed into one of the largest saltpeter-producing regions anywhere on Earth by the 17th and 18th centuries, supplying European trading companies with enormous, steady quantities of the mineral needed to keep entire national military arsenals reliably stocked year after year. An invention that began in a Chinese alchemy workshop had, within a few centuries, created an entirely new global trade network built around a single unglamorous mineral salt, one that quietly shaped colonial economics, taxation policy, and even military strategy, since a nation's ability to fight sustained wars became directly tied to how reliably it could secure a steady supply of this one specific raw material from halfway around the world. The flintlock mechanism arrived early in the 17th century, generally credited to a French gunsmith who refined the design into its recognizable modern form. The flintlock used a spring-loaded hammer holding a piece of flint, striking a steel surface to generate sparks directly into the priming pan. It fired faster than a matchlock, performed far more reliably in poor weather, and required no open flame to maintain at all, meaning soldiers no longer gave away their position in the dark simply by carrying a lit weapon, and cavalry could finally carry a loaded firearm safely without tending an open ember while mounted. Within a few decades, the flintlock had become the dominant firearm mechanism across essentially every major European military, a position it held for roughly 2 centuries, straight through colonial expansion and the wars that reshaped the modern world, carried by soldiers on nearly every continent long after the mechanism's original inventor had been forgotten by most of the people relying on it daily. Ignition mechanisms were not the only bottleneck engineers were racing to solve either. For most of the flintlock era, loading a musket meant measuring loose powder by hand, ramming a ball down the barrel separately, and hoping the whole sequence went smoothly under battlefield pressure. The introduction of the paper cartridge, a pre-measured bundle combining powder and ball wrapped together in a single paper package, cut reloading time down considerably, letting a soldier tear the cartridge open with their teeth, pour the powder, and load the ball in one continuous motion instead of several separate fumbling steps. It was a small logistical innovation compared to a completely new ignition system, but it mattered enormously on a real battlefield where the difference between reloading in roughly 10 seconds instead of 30 could easily decide who got the next shot off first, and, by extension, who was still standing once the smoke actually cleared. Entire training manuals eventually evolved around teaching soldiers a precise, repeatable sequence of movements for tearing, pouring, and loading a cartridge as quickly and consistently as humanly possible. The flintlock's roughly 2-century reign finally ended early in the 19th century, with the arrival of the percussion cap system, a small metal cap containing a shock-sensitive chemical compound that ignited instantly when struck, eliminating the need for loose priming powder, flint, and steel altogether. This final ignition innovation rendered every earlier mechanism, from matchlock to flintlock, essentially obsolete within a matter of decades, marking the last major milestone in a long, unbroken chain of refinement that had begun with a group of monks chasing immortality in ninth-century China, working with nothing more sophisticated than a fire pit and whatever minerals happened to be lying around their workshop. Looking back across the entire arc, from a Taoist alchemy workshop in ninth-century China to industrial firearms factories many centuries later, the story of how humans invented the gun is really a story about accident, accumulation, and migration unfolding together across an enormous span of time. Nobody set out on day one to invent a weapon. A group of monks searching for immortality stumbled onto a violent chemical reaction and very nearly burned their own eyebrows off in the process. Engineers and craftsmen watching that reaction unfold gradually realized its raw, chaotic violence could actually be channeled and controlled. First through a simple tube lashed to a spear, then through a properly cast bronze cylinder, then through increasingly sophisticated mechanical systems designed to ignite that same basic chemical reaction more reliably, more quickly, and with meaningfully less risk to the person actually holding the weapon. Each individual improvement, from bamboo to bronze, from open flame to spring-loaded mechanism, from loose powder measured by hand to a pre-packaged paper cartridge, solved a specific, concrete practical problem soldiers and engineers had actually run into while using whatever version of the weapon happened to come directly before it. None of it required one single flash of total genius. No lone inventor sitting alone in a workshop and emerging with a finished blueprint. It required centuries of patient, incremental refinement, carried across continents by trade routes, military campaigns, captured artisans, curious traders, and the kind of slow cultural exchange that quietly reshapes the entire world while almost nobody actually involved is watching closely enough to notice it happening in real time. The weapon that would eventually end the dominance of mounted knights, reshape the economics of entire colonial trade networks, and determine the outcome of wars across multiple centuries and continents began its existence as a mistake made by a handful of people who were never trying to build a weapon at all, tucked away in a mountain workshop, looking instead for something considerably more peaceful, a way to simply live forever.